Hey there everybody, this is a video from my Intro to Calculus class. We're going to move on to the next topic here. It's called higher order derivatives. And let's start by considering the slope of the equation f of x is equal to 3x cubed minus 5x squared minus x plus 1. So let's look at that equation and its graph. There. So looking at that, guess we should graph it. There we go. Looking at that. So it's a cubic, changes directions twice, but let's really think about what we used to do back in Unit 1 when we were talking about the change in the slope of this thing. This thing changes slopes a bunch of times. In fact, its slope is continuously changing. I really know there's only a couple of places where the slope is ever the same. I know that here there's a tangent that's horizontal, so that has a slope of 0. That has a slope of 0. So I know that right about here and right about here, the equation of the slope of this function, when I graph it, will have zeros. I also know that over here, it's got a positive slope. So I know that it's going to be coming this way. In fact, it's a positive slope that's slowing down. So it's going to be steeper, and then it's going to kind of start to round that way as it gets to this 0 here. And then once it hits this 0, it's still negative, right? It was a positive slope up here. It's going to be a negative slope after the 0 because now it's going down. And I can even kind of see that somewhere around here is about as steep downward as the slope ever gets. So somewhere around here there'll be a minimum for how low into the negatives the steep goes before it kind of comes back and then becomes positive again, starting about there, right where the 0 is. So if you can picture that, well, then spoiler, there it is. And we kind of already knew that. We knew that the equation for the slope from a cubic will be a quadratic. But now, here's something I don't know that we did do back in Unit 1. Now imagine the equation of this thing. Its slope. Its slope is going down, so it's a negative slope all the way until you get to here, and then of course you've got another tangent. So the equation line for this slope will be, let's see, negative until you get to about whatever that point is, and then it'll be a 0. So it's going to come up this way and then go up forever. And we kind of knew that too. We knew that the equation for the slope of a quadratic is linear. So here's something we've never done before. Let's think about those things algebraically. If we think about those algebraically, well, that first derivative was, of course, 9x squared minus 10x minus 1. So let's see if that's true. So let's see. I think this equation should be y equals 9x squared minus 10x minus 1. Yep, it is. And then, going back to my page here, I think that the next derivative, the derivative of this derivative, should be 18x minus 10. And let's see if that's true. Is this equation here, is this line here, really 18x minus 10? And yes, it is. So what we are now looking at is derivatives of derivatives. We call those higher order derivatives, and there's a bunch of different notations for this. Let's go back to good old Leibniz notation. Well, actually the first two, I guess the common ones are, instead of saying, your first derivative is y, then your second derivative is y prime prime, and then you could even do a third derivative. You could do a derivative of a derivative of a derivative. Think about it. The derivative of this thing would just be 18. And then, of course, in function notation, it's the same thing. The original function is this, and then when you do the derivative of it, you get f primed of x, and when you do the derivative of that, you get f prime primed of x, and so on, until you run out of derivatives. I guess if you really wanted to say f prime 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 of x, you'd of course get 0 because the derivative of a constant is nothing. So there's the kind of two common notations we use, but there's also Leibniz notation, where sometimes you'll see the second derivative look like this. It'll say d squared y over dx squared, which is kind of like saying the change squared of y over the change of x squared. This is also sometimes written like this, where you say the change with respect to x of the change in y with respect to x. So these two things say the same thing. Fancier notations, every once in a while you see one with a capital letter. Our textbooks don't use this. I think they mention them in one of the textbooks, but that sometimes is the second derivative, and this sometimes can be what you see for the second derivative. And of course, if you wanted a third derivative, so the derivative of the derivative of the derivative, you would just put a 3 there. But again, these ones you don't see very much. These are the big ones, right? This is Leibniz notation for the derivative of a derivative, and then that's the derivative of the derivative, and there's the derivative of the derivative. So, let's do some examples. It'll make more sense. Example 1 of our fancy new stuff is, let's find y prime primed of y equals x to the 5. So I don't know why I made such an ugly O there. There we go. So copy that one. Let's try this one. All right, so y equals x to the 5. So that means y primed equals 5x to the 4, which means y prime prime is 20x cubed. All right, pretty easy, eh? Example 2. Let's get you to do find f prime primed of x if f of x is equal to 4 root x minus 3x squared. Okay, oh, that one's not quite so easy. All right, so step 1, remember how we do these? Step 1 is, I think I'm going to change that into a notation that's easier to work with. And then step 2, f primed of x is going to be a half of 4, which is 2. And then that'd be x to the negative 1/2. 2 times 3 is 6. And then that's x to the 1. Which means that f primed of x is going to be negative 1/2 times 2, which is negative 1. Right? Half of 2 is 1. And then it's negative 1/2 minus another 1. And if you think about it, negative 1/2 minus 1 is like saying negative 1/2 minus 2/2, which is negative 3/2. And then the derivative of a linear is a constant. Right? Because think about it, that's x to the 1 minus 1, which is x to the 0, which is 1. So 1 times 6 is still 6. Right? That might not be the way that a textbook giving you a question like that might want an answer. If you wanted it back in radical form, you'd of course make that negative the 1 over the square root of x cubed minus 6. Okay? And if there's people who aren't sure how I turn that into that, oops, sorry. If there's people who aren't sure how I turn that into that, just message me through Edsby or something. I can always bring you on Teams and do a quick little lesson with you to show you how negative exponents and fractional exponents work. I always kind of assume that people coming out of grade 9 and 10 are pretty confident with this. All right, so there we go. Both of those are the same thing. Let's see. What else was I going to do with you? Oh yeah, one more. Okay, so how about we do one that involves plugging in a number. Example 3. Find f prime primed of 2 if f of x is equal to x to the 4 minus 2x squared plus 5. Okay, so what is this asking me actually? Well, it's asking me to, first of all, find the equation of the slope. Or find, maybe I should say that better. Find the equation of the slope of this line, and then find out how much that is when x is 2. So, let's find that out. First, let's find the first derivative, which is 4x cubed minus 4x, and then of course the derivative of a constant is nothing. The second derivative is 12x squared minus 4, And then f prime primed of 2 means replace the x with a 2. And that would be 12 times 4 minus 4, which is going to be 48 minus 4, which is 44. Okay, and again, just for fun, and because, you know, playing with Desmos is always fun, if I were to just go again, plug in, oh, I can't call this f of x, I already have an f of x, I'll just call it g of x. If I were to go, what was it again? X to the power of 4 minus 2x squared plus 5. There we go. Well, that's an interesting looking little graph. And I would like to find g primed of x. There it is. Makes sense that a quartic derives to be a cubic, which derives or differentiates to be a quadratic. And then I would like to know what g prime primed of x equals, what was it again? X equals 2. So I have there's a couple ways I can do this. I can actually enter x equals 2 and then just find out where those two things meet. And okay, let me zoom out. Here, let me get the other graphs out of the way. They're in the way now. Okay, and then I can zoom out and see that those, oh, I guess I should put this graph back. There we go. These two graphs meet at, there we go, 44. And if you don't feel like actually trying to find a point where those two lines meet, another way you can do this is you can actually just ask Desmos to figure out for you what g prime primed of 2 is. It'll tell you that it's 44. Okay, so that's probably enough examples to get you started. You should now be looking at working on the 2.8 questions and assignments. We'll give you today and tomorrow to work on them because, let's see, 2.8's got a fair number of problems here. Let's see. Well, it's only 1 to 10, but it's still a fair amount of work. So we'll give you today and tomorrow to work on that. If there's people who feel like working ahead because you get through these really fast, there is, of course, more of the same in the 4.5 assignment. And then, so that's, see, today's going to be, when you're watching this video, is Tuesday. So I would say give you today and tomorrow to work on 4.4, 4.5, and then Thursday I will post a new video that kind of prepares you for 4.6, but we won't really get into 4.6 till Monday. So really, you've got until Monday, because remember, Friday is actually a professional development day. It would have been an in-service day if we were in school. So you've actually got from now till Monday to work on 2.8 and 4.5. So that's a lot of time. So hopefully maybe that'll get you a chance to get caught up in your other classes if we're not going that hard. But then Monday we'll do a lesson where we get into exercise 3.1 and 4.6. And then that, I believe, is it. And we can start looking ahead to actually testing all this stuff. I still am waiting for some people to hand in the mini quiz from yesterday. Please message me on EDB and send me pictures of your work. The people who have handed it in as of right now being, what day is this? Monday evening. I've marked, I'm using air quotes like you can see me. I marked what you sent me, and I sent back through EDSB some comments, even if the comment was it's perfect. Just so you can read them. Please let me know that you're getting these comments. I'm still learning what it is that works for communicating with students. All right, that should do it. Good luck on the assignments, and again, look for another video on Thursday. Bye-bye.